Okay, it is April 23rd, Friday.
It is
April 23rd,
CS-030.
Friday.
It is
We're immediately in inception mode, so let me shut that down.
in inception mode.
So let me shut that down. In inception mode. So let me shut that down. In inception mode. So let me shut that down. In inception mode. So let me shut. All right. So work through our checklist as we're getting ready to start here. So I'm looking at the CS-030 checklist. Trying to get that set up for me here. All right, so first thing to do is I'm double broadcasting. That's first thing. First thing is to make sure the professor is only broadcasting on YouTube. Okay, I am broadcasting on YouTube. If all looks well, yep. Make sure your VPN is active so that you've got access to audio when you are in class. On campus, rather. Physically on campus. Find a quiet location. Tell your roommates you are in class. And they're going to need to shut down the sawmill they have as a side hustle. Excuse me. Turn off notifications on your phone and computer so you're not distracted. Speaking of distractions, let me turn down that music. All right, actually, let me just pause it. That's Up Fronts by Kitsa. All right, so music is off, turning off our notifications. I'm doing it on my phone, check, and on my computer so that I don't get notifications from my family about what my parents are doing that's nuts today. All right, put on your headphones so that you don't get echo if you decide to speak. Shut down any extra apps or browser tabs that you have floating around so you're not taking resources away from your in-class experience. I'm all set. All right, open Canvas so you can see what's going on. We have a couple in-class assessments today. And open Eclipse because today I am going to be sharing some code with you. And so I have got Eclipse open. I'm not connected via Saros, but I'm going to do that now. And I'm connecting. All right, open Firestorm and rebake your avatar. So that entails going under Avatar and Avatar Health and Force Appearance Update. Then make sure you've got your environment set up right. So go under World and Environment and set it to midday. Set your draw distance to a low number so you don't get a bunch of laggy behavior like what I'm experiencing now because I've got it set up really high. Set it down to about 200 for me. That'll work a little bit better. Go to the classroom, which is what I'm working on right now, and make sure that you can see your classmates' names so that you know who's talking. That's helpful. Check in at the attendance machine so that I have record of you being here, and or check in on YouTube if you're not able to get your client to work. So I see Ben F is there. I'm here by the attendance machine and looks like Taylor is jumping on top of Dee Dee. Dee Dodger seems to really like you. That's kind of sweet in a dogs are annoying kind of way. All right, we'll have him sit down. All right, and then test audio with a classmate. Okay, so here we are. It is April 23rd. Good morning. Let's see who we've got in class. See Trent and Sam, Dee Dee and Taylor. You're a ghost in the back. So if you could rebake, I'd appreciate it. Ethan, saw you fly in and drop into a seat. Good morning. Landon, good morning. Ethan, good morning. Matthew, Ben A, Morgan, Josh, good morning. Ben D, and Monty, good morning. All right, I graded the first Drone World assignment, and so you guys all did pretty well all around. Pretty happy with the way everyone was able to bring that together. I think some bragging rights are in order. Let me briefly just double check what those are. I'm going to fade out the YouTube for a second so that I don't show grades. Just want to make sure I got the first place correct. Pulling those grades up. Okay, so great. They're all set. Let me go back to broadcasting game. Okay, so bragging rights go to Didi and Frank for turning in their Bulo and Mugambage company. They delivered 10 ninjas on all 3 runs in the receiving the most number of points, so that's great. And overall, the lowest delivery time on average, which is what we were looking for. Second place, I had Landon, so good job with Amazon Company, and we'll continue to track that as we look at version 2 and 3, but everyone did fine on the assignment, so I'm proud of y'all, did a good job. All right, let me organize here. Let's take a look at Canvas to make sure we're okay with where we're at right now. I'm going to pull up a calendar and put a calendar down on the screen. Take me a second to organize windows. There we are. Okay, so today is Friday, April 23rd. We've got two class assessments due by the end of the day today. It'll cover the things that we're going to talk about today. And then Monday, you've got the third and final drone challenge. You have a technie due on Wednesday of next week covering tree structure. So that's going to require you to review some of the things we're talking about in the lecture via your textbook, and then you can take that technie in Canvas. And then, so drone challenge 3 will be a last programming assignment, and we will have a final exam during our final exam slot. It will be online, same as the other formats, except longer. It will be cumulative. It will be open book, open note, closed communication. There will be about 3/4 multiple choice and about 1/4 programming in various ways. All right. Any questions or comments before we dive into more tree work? All right, let's do some more tree work. Trees are awesome. All right, so to do that, I am going to shut down the calendar, and I'm going to bring, oh no, what I want to do is I want to get everyone in Eclipse. Yeah, we need that. Okay, so I am in Eclipse. I see some of you are there, and so for those of you that are present, I'm going to go ahead and share a folder, a project for today with you, and then I will share with the rest of you momentarily. Boom, 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 boom. Great. I am in Eclipse. Oh, yeah, I might as well show this to you. Nothing to hide. Well, oh, no, too fast. All right. Distracted, too much going on. All right, I'm sharing the project, and here's the code. Let me shut down all the extraneous windows. All right, here's the code I'm sharing, and let me share with one of you. Let me start with, let's just start with Trent. Make sure that works okay, and then we'll add the rest of you. Looking for a window that indicates to me that something's happening. Oh, okay, so Trent is getting a request to set up Saros and waiting to hear back. I'm expecting to get a little pop-up window that's gonna affect that sharing. So I'm kind of waiting for my pop-up window to show up before I share with the rest of you. Let me try one more. I'll share with Didi. Didi, I'm gonna drop a share with you. There we go, that's what I'm waiting for. All right. Just giving everything a second to connect. Looks like it's okay. Didi, does it look like it's sharing okay with you? How can I add Saros back to the toolbar at the bottom? To get Saros on the toolbar at the bottom, you go under Window and Show View and Other, and then you find Saros there, and you click on it, and it'll show up in one of your panels. All right, Didi, it looks like everything's going okay, so I'm going to add a few more folks. Let's go from the top, add a line, add you, make sure that that goes okay. Looks like that goes well, great. Ben Fernberg, let's add you. Okay, Ben A. That looks good. Carson, add you. Ethan Vaughn, we're going to add you. And Ethan Banez, we're going to add you. Okay, and Faith, we're going to add you. Josh, going to add you. Give those a couple seconds to settle. All right, Landon, going to add you. All right, Matthew, adding you. Morgan, adding you. Sam, adding you. And Trent, adding you. All right, and we'll do one more pass for 3 folks who don't look like they synced. Or let's see, Trent, you're currently waiting to connect. Not sure what that's about. Morgan, you're still working. Let's see, Ethan Banez, I'm going to try adding you one more time. And Faith, try adding you one more time. Trent, looks like you're in. And looks like we're waiting for Ethan, Faith, and Trent. Something going on your computers or my computer or our connection. All right, we'll let that settle out. And we'll carry on smartly and hope for the best there. Let's see. There we go. Faith got in. Great. And do. Okay, we'll take a look at some other, we'll come back to that in a second. What we left off talking about was trees, and we're going to pick up on that. And so where I want to start here is just reminding ourselves about how trees work. So a binary tree was a special case of a tree. We have a tree structure is an abstract idea. It's a way that we keep track of data in our head. It is roughly modeled on an ideal family tree where you have a root, which would be one person, and then all of the descendants that follow from that person. We use that family tree metaphor in order to talk about various relative positions in a tree, acknowledging that no family is actually like that, of course. Also, the tree is weird in computer science because typically we put the root at the top and at the bottom are all the leaves, and that's just a vagary of our visualization. And at the end of the day, we don't really end up visualizing our trees very often. So the tree is a data structure, and we have to mentally keep track of how that works and how we move around the tree. But we don't actually draw the tree very much. We just use the structure of the tree in order to accomplish different kinds of algorithms faster than we might if we were only using, for example, an alternative data structure like a linked list. A linked list can be considered a kind of degenerate tree. A linked list is like a binary tree that only has left elements, and it ends up having the same structure. But in a binary tree, we have two children for each node, a left child and a right child. And so this picture is sort of a visualization of that, where you've got a mom and two children, one child on the left and one child on the right, and only two hands. I guess the metaphor kind of breaks down. The mom has two hands and therefore a left and right child. Maybe she has more kids. She only has two hands regardless. All right, so that's a binary tree. That's in contrast to the tree that we see in our code under section 1. Under section 1, you see we have a tree that has arbitrary numbers of children. So if you go to tree.java and you look at line 15, you can see that there's a definition of a tree that has an interior class on line 12, which has two instance variables, a data element that's keeping track of some data, and then a list of children. And so this is in contrast to a binary tree. This is a tree in which each node can have an arbitrary number of children. And so we can do different kinds of work with this structure. And there's an example of what we looked at last class in the tree demo class. The tree demo class we talked about using the slides, but we didn't run it. And if you do go to tree demo and you run it as a Java application, you can see how a tree gets constructed. We never actually draw the tree. We just create that data structure of a tree. We have to use it correctly, and we have to mentally visualize it correctly, and then we can do various operations on it, like calculate the size of the tree. So this is a tree that we reproduced part of that British royal family tree. And it has a size of 4, meaning that it has a size of 4 different nodes. And we solve that recursively. If we go to the tree data structure and we click on size, we can do F3 to jump to the definition of size. And then we'll jump into the code where size is calculated. And you can see that it is, we have two sizes. We have a size which is in the tree, and we have a size which is in the node class. So we can jump between those on the right on the outliner view. So if we start in the tree version in tree.java line 60, which is what we call in our tree demo class. Let me put those side by side. So on the right, when we ask what the size of the tree is, we make a recursive call that starts in the tree.size method. And what we do is we say, well, is the root of this tree, let me format that up. It was formatted for slides, but not for code. Yeah, that's a little cleaner. So if we see that there's no nodes in this tree, if our root is null, then we're just going to return 0 because we have no data. But if there is data, then we're going to launch a recursive process in our node item that's going to recursively look and track down all of our different nodes and calculate the total size. So we're going to call root.size. Let's look at the definition of root. That's at line 10. It's simply an instance variable, which is a reference to one node, the root node. So now I'm going to go back. I'm going to go back to line 65 in tree.java, and now I'm going to select size, and I'm going to hit F3 on that to jump to the definition of the size method in the node class. The size method in the node class is different size method. This is the one that we're calling and launching our recursive function. Let me reformat that so we can get it all on there. Save that. By default, we're going to say that our size starts at 0, and then what we're going to do is we're going to recursively add up the size of all of our non-binary children. And we're going to do that by going through our children one at a time and asking each child recursively, hey child, what is your size? And that's going to dig down deeper and deeper and deeper until eventually we get to some node that has no children, and then we will not run the loop on line 24. So our ending condition is when we get to a node that has no children, because line 24 therefore will not get run, and therefore line 25 will not get run. Well, 24 does get run, but there's no children. And so line 25 does not get run because there's never a child to assign to one of the children in the list. So child.size isn't called recursively, and so it's as if when we get to our child node, it's as if we never execute that. And in our child node, we end up with sum equals 0, and then we add 1 to that sum for the node that we're currently at, making our totals 1, and then we back out. And when we back out, our parent class now adds our size 1 to the 0, and then iterates through all of our other children, asking each child in size what it is. Child might be 1, it might have multiple children. Our tree isn't all at the same depth in this case, so some children may have a larger size than other children. Eventually, we go through each of our children, recursively asking them each what their size is. We sum them up and then return them to our caller with 1 additional count for our size. So that's how we do it when we are working with a non-binary tree. In a binary tree, we have a slightly different kind of definition. So let me jump now to section 2, the package section 2. And I want to show you how the binary tree is structured here. So this is our binary tree class, and you can see that there is an I am now looking at binarytree.java. That's in section 2 of the code that I'm sharing. There's an instance variable, which is a reference to a node class, and it's also called root. So just like our non-binary tree, our binary tree also keeps track of a root. What's different is when we get down to our node class, that is, I'm going to use the right side, my outliner, to jump right to the embedded node class. You can see that our embedded node class has the data that it's storing and 1 link to the left and 1 link to the right. So let me remind you that when this wasn't a binary tree, what we had instead was we had something like this, where we had a list of children instead of a left and right. So what you can see is instead of having an arbitrary number of children, we are breaking out that list into just 2 references explicitly left and right. And we're going to use that structure in order to do our work. All right, so one of the things that we said is we could use a binary tree for is a decision tree, playing a game of 20 questions. And we can treat each node as if it is a question, and then each interior node as if it's a question, and each leaf node as if it's an answer. And if it's a question, proceeding down the left node corresponds to answering that question yes, and proceeding down the right node corresponds to answering that question no. Here's a little example of how we might build that. A tree structure where we ask first if it's a mammal. If it is, we ask, does it have stripes? If it doesn't, we declare that it's a pig. Or however we traverse this particular tree in order to arrive at a particular answer. It's pretty good. This is a real basic example of machine learning, to be honest. The difference between using a decision tree to answer a game of 20 questions and machine learning is that in machine learning, you write an algorithm for the computer to build this tree. And that's like the 3rd machine learning algorithm that you learn in any typical machine learning class. It's actually really effective. Decision tree is a remarkably effective way to have a computer make decisions. So let's take a look at a decision tree in code. And so if we drop into our code set, let me just see if there's anyone else we need to invite along here. We'll bring along Ben D and Ben A and Frank and Trent again, and see what comments we've got in class about that. It says, how can I add SARS back? We did that. Can you reshare the project with me? My Eclipse crashed. My Eclipse cached. Wow. Hope it cached for a lot. I know what you mean. It crashed. All right, so adding you folks in, taking a look at progress, make sure you're all right. Looking for, if I am not able to set read only, be careful about the code, because unless I manually set read only, you can edit it, but so far so good. All right. Great, looks like everyone was able to join. All right, so let's take a look at our decision tree demo in section 2. Open up decisiontreedemo.java, and you can see some code that's going to implement a decision tree for us. And before we look at how it works, let's go ahead and just run it so we get a sense of what's happening. So in decisiontreedemo.java in section 2, I'm clicking on main and I'm going down to run as, and I'm running it as a Java application. I'm switching my view to console so I can interact with the program. And you can see that it's asking me, is it a mammal? Yes, it's a mammal. So I'm going to type in yes and hit return. Does it have stripes? I say no. Hit return. And it answers it is a pig. So my algorithm here, my program, is playing a game of 20 questions with me based on a tree that I have built. The program is done now. That's right. Okay. So let's look at how this happens. If we go into main, we can see that we're building, the first thing that happens in 12 is we build a question tree. And this is going to build a binary tree. So let's look at what the constructor for binary tree looks like. I hit F3 after highlighting binary tree. You can see that the construction of a binary tree involves what data we want to keep at the root, what tree we want to link in on the left, and what tree we want to link in on the right. The constructor creates a new node object for our root. It sets the data equal to the data that the constructor received when it was called. It sets the left of our root node to whatever the tree was on the left. But notice it doesn't set it to left. It doesn't say root.left equals left. It says root.left equals left.root, which means it's going into the left tree, finding the root of the left tree, and grafting it in. This is important because root.left is a reference to a node, and left.root is also a reference to a node. We have to make sure that our typing is correct. And what this is doing is it's for the people that are, for the users of our class, it is presented as a binary tree object. But for whenever we're doing implementation, we're always working with the interior node objects. And that's part of the implementation. It's not part of what the user sees. It's part of how the implementation connects everything. There is no tree object internally within a binary tree. There are only node objects. And so whenever we do a constructor like this and we're given a tree as the way to kick this off, the implementation extracts the nodes from that tree in order to graft it into the tree that we're building. This constructor may be receiving a tree that has lots and lots of nodes, left side or right side. And that's fine, because when we graft in the root of the left tree and the root of the right tree, we pull with that all the references and all the children references that are part of that object. They come with that reference. All right, so let's go back to where we're constructing our tree and see what's happening here. This is a little tricky. It is using a bunch of trees that we're creating with constructors. And so what's happening here is we're creating a new binary tree. This is our roots. Our question tree is going to keep track of the top level tree. We're going to pass in the object, is it a mammal? And on the left side, we're going to pass in another binary tree that we're constructing on the side that says, does it have stripes? So that means that that's the yes answer. And on the right side, we've indented it so that we can see what we're doing here. That's not part of Java, but it's nice to see. On the right side, we ask, does it fly? And the tree that we construct on the right side is going to have as a left side, it is an eagle, if it is not a mammal and it does fly. And if it does not fly and it's not a mammal, then we ask, does it swim? And if the answer is yes, it's a penguin. If the answer is no, it's an ostrich. So we're calling constructor after constructor after constructor here, and we're just immediately passing it into the previous constructor. We're not keeping any independent references along the way. We could, if we wanted to, we could have done something that looked like this. We could have asked, well, I guess at the bottom we would have said, sorry, my editor is breaking. We could have called an alternative constructor, which is what we're doing down here, that takes no children because it's a leaf node, so the children get assigned null. And then we could have done another one and said, oh, I guess we're saying it is an ostrich, sorry. And we could have built it up backwards from the bottom up. And if we did it like this, what we would be doing is each time we created a tree, we would be creating a reference to it. And then later on, we would create a new tree in which we pass in that reference. And so we temporarily store this tree in a reference called A. We temporarily store this reference in we store this tree in a reference called B. And then we construct a new reference C, which is composed of B and A. Instead of doing this, we just take this code right here and we immediately put it into A and B. So you can actually have Eclipse do that if you go under source and inline. Oh, sorry, refactor inline. And you can see what I did is I just moved the A directly in there. So now I'm not keeping a reference to it because I don't need it any other place. Refactor inline. And what we end up getting is this code right here, just not formatted nicely. So all we're doing is constructing it on the fly. It's just convenient. Sometimes I don't know if it's easier to read or not, but with the indentation, it's fine. All right, so that's the data structure we're working with. That's our game. That's our AI. That's our intelligence. That's our model. That's our model of the world. And now we work on the user interface. We create a semaphore, which we've seen before. We create a done flag, which says whether or not the user is done entering something in. We create a scanner, which really pet peeve. Really should be like that. There we go, formatted, save. All right, so we create a scanner called in. By putting it in a try block, we automatically close it no matter what happens with exceptions or anything else. And then within the body of this while loop, we say while we are not done, and since it starts false, this initially is true, so we're going to run it. We are going to grab the left half of the tree and the right half of the tree, and we're going to check to see whether or not it is empty or not, in which case we have an answer. And so if we have an answer, we're going to go ahead and print out the answer, and then we're going to set done equal to true, so we're going to stop going through our loop. So this is sort of like the loop. We're using a loop instead of a recursive style of going through the tree, which we could have done as well. If we're currently not looking at the bottom of the tree, then we're going to ask a question. And then we'll create a local variable to capture the user's response. The question that we are going to ask is we're going to take the current reference that we have. We're going to pull the data out, which because it's not a leaf must therefore be a question. And we're going to say yes or no, yes or no. We'll grab the response from the user by asking them to enter in their next token. We'll convert it to uppercase to restrict the number of conditions we need to check. We put it in a do while loop to make sure that the user enters something that's valid. So in order to get through this do while loop, they have to answer a Y or an N. If they answer anything else, it'll just ask them a question again and again and again and again until they comply with our instructions. Once they have complied with our instructions, we check whether the answer is yes or not. And if it's yes, then we move our reference down the left-hand side of the tree. So that question tree is no longer at the top of the tree, but it's walking down the tree on the left side. The question tree reference is now the left or the right, depending on how the user answered, and we go through our loop again. We look at what the left and right side of the current point that we're at in the tree is. If it is a leaf, we put the answer out on the console, and if it's not, we ask the new question that's present in the tree. Once we've gone through this entire loop, we have at some point gotten to a leaf, output the result, done has been set equal to true, not done is false, we leave the loop, we close the scanner, we exit the program. Along the way, because we're using question tree as our reference to walk down our tree, we do lose a reference to the top of our tree. But since we are running this program one time, it doesn't really matter so much. So let's add one more question to our tree here. Let's say that we ask if it's a mammal, we ask if it has stripes, we ask if it's a carnivore. If it has stripes and it's a carnivore, it's a tiger. If it's stripes and it's not a carnivore, it's a zebra. All right, let's see. It's a mammal and it doesn't have stripes. So there are lots of mammals that don't have stripes. Someone want to throw another mammal that doesn't have stripes in? Someone audibly say that out loud so I can hear it. Animal without stripes. A whale. An animal without stripes, a whale. Great. All right, so let's say we know that we want to have whale as an answer. And so we need to differentiate between those two. So on the right side, if it's not a carnivore, we're going to say a new binary tree, and we're going to ask a question that differentiates a pig and a whale. And we'll say, uh, does it have a blowhole? And if the answer is yes, then it is a whale. And if the answer is no, then it is a pig. And then we just need to close out our constructor there. I did it the wrong place. Let's see. There. I'm just matching up parens here. Boom, boom, and then one more. There we go. Boom, boom, boom. Okay. And so now, having written that, we should be able to run our decision tree demo and have a new question. So let's run it as Java application. Is it a mammal? Yes. Does it have stripes? No. Does it have a blowhole? Yes, it is a whale. And so we can continue to add components to this as long as we want, and create quite a sophisticated decision tree that does a really remarkable job at getting things right. All right, questions about any of this code? Let me give you just 60 seconds to look at it and see if you have any questions about what's happening. And if not, we will carry on smartly. Yeah, I mean, I see that. Yeah, so is there a less finicky way to construct the decision tree? All the commas and parentheses seem easy to screw up and get confused. Yeah, I mean, if you were making some kind of an application where a game or something, you probably wouldn't construct it in the fly like this. You would probably build it in a file, a separate file, and then you would have something that parses that file and constructs the tree as you parse the file. Because you don't, if this gets really big, you don't want to have your code dominated by what's effectively data. You would want to keep your data in a separate file and then bring it in. So yeah, I would, if this got much bigger, I would refactor the program so that there's a data file that you read in and turn into a tree with a loop and a file scanner, kind of like we did when we were reading in the, what were we reading in? When we were reading in the CSV file for the country data, is that right? Yeah, when we were doing this, when we were learning how to do sorting, arbitrary sorting using the compare to method, we had a helper method that would read in data from an external CSV file. And so I would do something like that if I was making this much larger. This is yeah, I think that's right. Good question. Any other questions? There are no dumb questions. There are only questions that are extremely rarely asked. Okay, that's a decision tree and how we can work with that. A decision tree is one example of how we can use a binary tree. Another example of how we can use a binary tree is as a Huffman encoding tree. A Huffman tree is a way of compressing a file. And what it does is it presents an, let's see, I don't know if maybe as a younger person you ever got into ciphers. A cipher is a way of encrypting a message. Like you might want to write a note and you might want to write a cipher. And the way the cipher works is that you substitute out one letter for another. So instead of writing down an A, maybe you write down a G. Instead of writing down a B, maybe you write down a Z. And so that there's a table that helps you decipher or decrypt the message that you have sent to someone as like a game, I mean, it's not just related to childhood, but you usually encounter it in childhood first. And so you need to have this table that helps you to decipher an encrypted message. A Huffman tree is like that. What a Huffman tree does is it helps you to decipher and compressed message. And so the goal of a Huffman tree is not to hide information from someone in the way a cipher is, but the goal of a Huffman tree is to compress information, to keep track of information in a smaller size file than in other files. And actually, a Huffman tree has been proven to be the most that you can compress a file without losing data, in a couple constraints about what kind of file you're compressing, et cetera, et cetera. And so the way the Huffman tree works is it uses a binary tree. And each one of the leaves on the binary tree has the symbol that we want to encrypt or encode or compress, depending on how you want to think of it. And the way that we decide how we're going to compress that particular symbol is we're going to walk along a path starting at the root of our encoding tree, our Huffman tree. Starting at the root, we're going to walk down the tree to our leaf, and along the way, we're going to write out every decision that we make. If we go left down a path, we're going to write out a 0, and if we go right down a path, we're going to write out a 1. So let's visualize this and take a look at what this looks like. Here's a Huffman tree that encodes the 13 characters from the Hawaiian alphabet. So the Hawaiian alphabet uses the same characters as the English alphabet. The Hawaiian language alphabet uses the same characters as the English alphabet, but there aren't 26 of them. There are only 13 of them. And so this is a Huffman tree that can be used for compressing Hawaiian text. And the way it works is you start at the top and you find the character that you want to encode. So let's say we wanted to encode the word aloha, which is, a Hawaiian greeting and whatever the opposite of a greeting is, a departure. So to do that, we have to find the A. And so the A is located here. So the way we're going to compress or encrypt the A is we're going to write the A as 1, 0. The next thing that we have to write down is we have to write down the L. So following the 1, 0, we're going to write down 0, 0, 0, 0. So 1, 0, 0, 0, 0, 4 zeros. After the L, we're going to write down the encryption for O, 0, 0, 1. That's O. Then we're going to write down the encryption for H, that's 0, 0, 0, 1, and then A again, so 1, 0. That gives us a sequence of characters that we can read into the same tree in order to construct the result. So let me see. I kind of want to dig into that just a touch more. In order to do that, I need to get a window up where I can show you what's happening, and a good window would be MacVim. Okay. All right, so let me change the way my windows are laid out so that they are side by side so you can see what's going on. Let me convince my computer that it should participate in what I'm doing. Let me restart my window layout manager. See if that helps me at all. Okay, well, come on. All right, let me just try and manually do this. See how long that lasts before it decides to reset it for me. Oh, there it goes. It reset it right away. That was really great of you. Sorry. There we go. All right, so what I said is that we're going to encode aloha. So on the right, I'm going to write down the characters, A-L-O-H-A, and now I'm going to translate them into bits. So here's 1, 0, that's the A. 1, 2, 3, 4 is the L. 0 is 1, 2, 0, 0, 1, that's the O. The H is 0, 0, 0, 1, and then the A is the same characters there. So one thing to note is that by default, characters like this take up 8 bits. So if we were going to encode this in the normal ASCII encoding, it would take up a total of 8 bits. And so this would be 8 plus 8 plus 8 plus 8. So that'd be a total of 5 times 8, or 40 bits that would be necessary. In contrast, what we've done here is we've taken the same string and we've encoded it in 1, 2, 3, 4, 5, 6, 9, 13, 15 bits total. So we have achieved a pretty good compression here. Underlying this is the choice of how to make this tree, because you can see that some characters take less bits to encode. For example, the A takes 2 bits to encode. But if you look at the W, the letter down at the bottom right, that would be required in order to, for example, spell Hawaii. That takes a lot of bits. It takes 1, 2, 3, 4, 5, 6 bits, it looks like. The height of our tree is 6. Or 6 minus, the height of the tree is 7, but minus 1. It's 1, 2, 3, 4, 5, 6, 7. Yeah, so 6 bits. So a W would take 6 bits. So an A takes less bits and a W takes more bits. This difference in the number of bits that it takes to represent a character is the fundamental insight of how compression happens. So in the standard encryption, each character takes 8 bits regardless of which character it is. In a Huffman tree, each character takes a variable number of bits. The way you choose where characters occur in a tree is by looking at their frequency. So what's built into the Huffman tree is an encoding of how frequent different characters are. So very frequent characters get placed higher in the tree so that they use less bits in order to encode them. So imagine that you had a document written in English using English characters, and you were going to create a Huffman tree encoding for that using all 26 characters of the English alphabet, maybe a few more for uppercase and lowercase and punctuation. What you would want to do is to have characters like S and T and R, characters that are very frequent in the English alphabet, to be able to be represented in a small number of bits. That's how you get compression. Rare characters, for example, maybe a capital Z or a percent sign, you want to take more bits. In fact, you might even want to have them take more than 8 bits. Because they're so rare, you're going to get a big win by encoding your frequent characters with less bits. Now, what's interesting about this is that there's no ambiguity in the decoding process. So because it's written in a tree to start with. So if we were given a sequence of bits like this, and we didn't know what it was going to encode, we would use the same tree in order to decode it. So we would start with a pointer here on the 1, and we would walk down our tree. And we'd say 1 goes to the right, 0 goes to the left. And now we are at the character A. And once we've gotten to a leaf, we start over. And we start with our zeros, and we say 0 goes left, 0 goes left again, 0 goes left again, 0 goes left again, and we have an L. Then we go to the top of the tree, and we start again at the top of the tree with where we are in this stream of bits. 0, 0, 0, no, 0, 0, 1. Oh, that's an O, so we write down the O. And now we start again at the top with whatever bit we are at in the stream. 0, 0, 0, 1. That puts us at H. Oops, take that H. And then finally, we have a 1 and a 0, which encodes the A. And so it's not, as long as you have the entire bit stream, and as long as you are using the same tree in order to encode and decode the message, there's no ambiguity about what characters are encoded here, even though it kind of looks like, oh, but what if you started at a different place? Well, that's true. If you start at a different place, it's a different encoding. But as long as you start at the actual beginning, you're going to get the exact same word every time. So this is the basis of a way in which you can use a decision tree in order to do something much more sophisticated than kind of most of the toy examples that you see in an introductory programming class. And like I said, although there's a little bit of more sophistication that's required in the process of building this tree, and perhaps storing the tree, zip files use a method like this in order to encode the content. So if you ever encrypt something, or sorry, if you ever compress something using a zip file format, under the hood, what's happening is a Huffman tree style encoding. There are a few more nuances to make it even more efficient, but that's the basis of it. Questions or comments about the Huffman tree? One of the questions for the assessment today is going to ask you to do the encryption-decryption process that I just did. Check in. It's true that when like a zip file has to store the tree at the beginning of the file in order to know what tree is being used to encrypt or decrypt it. It's not really the tree size that determines whether it's worth it or not. What determines whether it's worth it or not is something called the entropy of the file. Entropy is a mathematical analysis, a mathematical definition of randomness. It is formalized, so it's not just like some ethereal idea of things in the universe are random. It's a specific discipline called information theory. The whole field was introduced by a guy named Claude Shannon early in the days of computing, and information entropy talks about how much compression is possible in a file. And the intuition of this is that if every character is equally likely in a particular document, you have the same frequency for every character, Z's, A's, S's, T's, then you're not going to get any benefit from compression. You really can't compress it because there's no, you have high information entropy, and so there's not a lot of opportunity for compression. In contrast, if your file was completely consisted of one letter, you have very low information entropy, and you get very high benefit from being able to compress something. So you may have encountered situations where you do something like try and compress an MP3 file, or you try and compress a video, or you try and compress a JPEG image. Because those files already have done compression in them, you reach a point of diminishing returns where you can't compress a compressed file, right? You can't just keep compressing compressed files until you get down to like a 1-bit file and then be able to reproduce the file that it came from. That's because you only get any benefit from compression if there is information entropy, if there's low information entropy in the file to start with. So that's a roundabout way to answer your question. Your question was, do you get, let's see, is there a point at which it's not worth doing compression? And the answer is yes, and it has to do with how much randomness is in the file. The less randomness in the file, the better benefit you get from compression. So we got a couple other comments here. Sorry, go ahead. Yeah, yeah, that totally makes sense, and it is accurate that if your string that you want to compress is small, there's like a limit to the amount of benefit that you can get, and adding the tree that's used to compress and decompress it is going to eat up that benefit that you got from doing compression at all. But the tree is relatively small, and so you don't need a very large file before the benefit that you get from doing compression is much greater than the size of the tree that you need to compress it. So I mean, like just like a kind of a gut sense, like if you have a file that consists of 2 paragraphs of text, you're going to see some benefit. 2 paragraphs of like language, not 2 paragraphs of random characters. But if you have 2 paragraphs of language written out, like an essay or something, you're going to see that it would be net worth it in order to compress, in the sense that you will see compression even though you have to store the tree with it, because you just really, really quickly get a lot of benefit from compression. As the size of your file gets larger, the benefit that you get from compression grows and grows and grows, but the dictionary always remains the same size. So it's just an issue of how large a file you're compressing at when you start seeing a net benefit for compression, and it's just not very high. It's a couple paragraphs maybe, if you have an efficient encoding of your tree. Josh, I'm glad that you see you're happy we have some zeros and ones. Hang around for CS-045. You'll see a lot of zeros and ones. Okay, here's another thing that we can do with a decision tree. We can use a decision tree to represent arithmetic operations. And what we're going to do for this decision tree, what we're going to call this kind of decision tree is an expression tree. And an expression tree is a way of representing an arithmetic expression. And it's, pretty straightforward how you convert an arithmetic expression to an expression tree. It is a hierarchical, arithmetic expressions are hierarchical, and so representing them is easily transferred to the tree. What you need to recognize is that interior nodes of an expression tree are operators, and leaves of an expression tree are numbers. And so if we wanted to, for example, encode paren 3 plus 4 paren times 5, where we do the expression 3 plus 4 before we multiply times 5, we would do it with an expression tree like shown on the left, where the bottom left subtree is 3 plus 4. And you can see that we do that expression by looking at the 3, going to the parent, and going down to the child. And we can resolve that expression tree, or this bottom chunk of the tree can be replaced by a 7. And then if we put a 7 here, we could resolve this tree by saying 7 times 5. And then we could resolve the entire tree and replace it by 35. In contrast with the expression 3 plus 4 times 5, the way that we do our arithmetic operations is we recognize that times binds tighter than plus. And so without the parentheses, we want 4 plus 5 to be executed first. So even though the digits are the same on the left and right, the trees look different and they reflect the different order of operations. So on the right, we can see that the 4 times the 5 has to be executed first. That gives us a 20. So we can replace this subtree by a 20, and we get 3 plus 20. And the result of evaluating this entire tree is 23. That's reflected in the different order of operations, and the different order of operations is reflected in the different structure of the tree. So an expression tree is an elaborate expression tree is how Java does its representation of a program. So when you type programs into Eclipse, what the Eclipse IDE is doing in conjunction with Java is creating an expression tree that includes all the different operators that are present in Java, not just arithmetic operators, but loop operators and function calls and everything else. And that entire tree is how you get the static analysis. When the tree isn't working, when it can't construct a tree, that's when you get the errors in Eclipse, and it shows you a little red icon on the left because it can't make a tree out of what you've got. All right, so expression trees, we can write them down, we can evaluate them. That's 3 different examples of how you can use a binary tree. You can use it as a decision tree, you can use it as a Huffman encoding tree, you could use it as an expression tree. All of them are based on a binary tree, and all of them are different things that you can do with the tree, and you can use them if you'd like in a particular example. You can encode them. You can write a program that uses a tree in that way. Let's use a binary tree, but let's put an additional constraint on it and create a new kind of data structure. That data structure is going to be called okay, I got a little ahead of myself. We're going a property of a tree before we get to that new data structure. A property of a tree is whether or not it is balanced or not. A binary tree can be balanced or it can be unbalanced. What makes a binary tree balanced is that both its left and right child have approximately the same number of nodes. So if you think about this like a weight scale, like a scale of justice, or a gold scale, or whatever quarter scale that we see in the picture here on the left, we can imagine that the 2 children are the left and right baskets, and in a balanced tree, the left and right side will have approximately the same number of nodes. This property of being balanced is helpful for being able to analyze different kinds of algorithms. Here's an example of 2 trees that are balanced and unbalanced respectively. So the red side is balanced. The left and right side have approximately the same number of nodes. In fact, I think they have exactly the same number. Oh, no, they're off by 1. Yeah, off by 1. And the right one is very unbalanced. It is much heavier on the right side than it is on the left side. And you can see, if you think about the example on the right side, if we got rid of this node right here, it would still be a tree, but it would have exactly the same structure as a linked list, where each node connects to one follow-on node, which connects to one follow-on node. Unbalanced. Blue is unbalanced, red is balanced. How balanced does it have to be balanced? Well, A rule of thumb is that it can't differ by more than one. And that's because if you have an odd number of nodes, it's difficult to balance, or rather, if you have an even number of nodes, it's difficult to balance the left and right side. And so we say balanced is, within a weight of 1. So when we have a balanced tree, there's some math we can do that helps us to think about the structure and shape of the tree, because again, we don't visualize this tree when we're programming with it. We have to deal with it in terms of its properties. So here are some things about a balanced tree. If you have a balanced tree, a binary balanced tree of height h can have 2 to the h minus 1 nodes. So let's look at this tree here as an example. This is a binary tree because every node has one left and right child. It is a balanced tree because every node has exactly the same number of nodes on the left and right child, even though the number of left and right nodes from the root is different than the number of left and right nodes on this subtree here. For any given subtree, the left and right nodes are equal. In that case, we see that our height is 1, 2, 3, 4, or the number of nodes on the longest path from the root to the leaf. There are no paths that aren't 4, it happens to be in this perfectly balanced binary tree. And in this tree, we end up having a total of, 15 nodes. 1, 2, 3, 4, 5, 6, 7, 8, plus 4 is 12, 14, and 15. Our height is 4. 2 to the 4 is 16. Subtract 1, the number of nodes in this tree is 15. So it's not, it's a sort of, the fact that this has 2h minus 1 nodes, that the number of nodes that is in this tree is based on a power of 2, is reflective of the fact that we have a left and right, and that idea also gets echoed in choices between zeros and ones. So the reason why powers of 2 show up so much in computer science is because at the very root we have zeros and ones, or choices of 2. And we see that same kind of structure happening in a binary tree because we have a choice between left and right. So powers of 2 show up in different ways. So we say that this is a completely filled binary tree of height 4 because every path from the root has a height of 4, and as a result we have 15 nodes. You should be able to answer a question. In a perfectly balanced binary tree of height 5, how many nodes are there? 31. That should be a straightforward answer. The flip side, you can do the flip side analysis too. You can say, hey, if my tree has 63 nodes in it, and it's a perfectly balanced binary tree, how high is it? Well, 63 would be n. That's how many nodes are in your tree. You add 1 to that, you get 64. 2 to the 6 is 64. And so your height is 6. The height of a completely filled binary tree with 63 nodes in it is 6. And so for a balanced tree, your height is going to be approximately log base 2 of the number of nodes in your tree. You can see we've gotten rid of the 1 and we've given an approximate, but that's roughly what we end up getting. So for example, if you have a balanced binary tree with 1,000 nodes in it, the height is about 10 because you're going to have 2 to the 10 is 1,024, which is about 1,000. The height of a balanced binary tree with 1,000,000 nodes in it is about 20 because 1,000,000 is 2 to the 20th power, about. And so we have the power of 20. And that means that if you had a decision tree, imagine you had a decision tree and you have 1,000 nodes in it. It means that you can answer any question in 20 questions. You can solve any 20 questions game in 20 questions because your tree has a height of 20. The first one, second one, third one, and then finally you get down to the bottom of the tree, height 20. That's your 20th question, and your 20th question is it a pig or is it a whale? And so that means that you have 1,000 nodes in that tree. That means that it takes about half the nodes in order to get to the bottom. So you have about 2 to the 10 different questions you can ask. And that means you have about 2 to the 10 different animals that you can represent. So that means that in a decision tree where you're playing the guessing game for an animal, you can have 1,024 different animals represented in that tree. And if a person had in their head any one of the 1,024 different animals, your machine learning algorithm, your program has enough space to be able to get the answer to that question. If your user can think of an animal that's outside of that 1,024 different animals, it's possibly the case that your program can't get it right because you just don't have enough representational space to ask the questions to differentiate that many animals. So you'd have to change the game to 21 questions instead of 20 questions. And as soon as you change the game to 21 questions, well, now you get 2,048 different animals you can represent. So each additional question that you're allowed to ask as a computer doubles the number of animals that you can represent. So there it is. All right, so we are out of time. What I have given you, what I've also shared with you in the code today is a representation of a binary tree. Let me see if I can just make sure we've got that there. Binary search tree. Okay. All right. So we'll take this idea of a binary tree, our binary tree implementation, and on Monday, what we're going to do is we're going to add that additional constraint that I foreshadowed there before I had a chance to talk about too early. I needed to talk about balance trees before I introduce that additional constraint. We're going to introduce the idea of a binary search tree, which is a binary tree that has an additional constraint on it. We'll get there. All right, so today, don't forget that there are 2 assessments about the work that we talked about today. You can find them under Canvas. They're actually published, and I can drop that in game for you. They're on Canvas, so you don't need this link, but if you happen to be in game, I'm going to drop it here. There you go. And actually, hang on one second. Sorry for the delay. All right, the second one is about binary search trees, so I'm going to move that forward. That's not going to be for today. So you have 1 assessment due today, and let me just adjust the timing on it. Stand by. Great, the timing is now Monday. Okay, so you have 1 assessment due today. The second one on binary search trees is linked in Canvas, but if you look at the due dates should be correct. They should be correct on your calendar. If I look on the calendar, I want to believe that. Help me to believe, Canvas. Help me to believe. Looking at 30. Yep, everything's good. Thank you for your attention. Any final questions or comments before you are released? All right. Thanks for your attention. Don't forget to sign in on the attendance board if you didn't do that. And have a great weekend. Study your trees. We've got an exam coming up. Don't wait till the last minute to make sure you fill in all the details of the stuff we've been studying if you missed one or you got lost in a particular topic. Take care.
Okay, so Dr. Patterson, as you're talking about that, the 2
Anyone else? So let me shut down, I'm double broadcasting. Let me shut down the YouTube feed. All right, so this has been April 23rd, Friday, CS-030, and we are shutting down our YouTube broadcast. Let's take care of that. YouTube broadcast. Let's take care of that.
Dr. Patterson?
All right, April 23rd, shutting down the YouTube broadcast. Thanks for your attention. Shout out to all the folks around the world who happen to be watching this class. Thanks for your attention. Shout out to all the folks around the world who happen to be watching this class.